Hi, I'm Ashruja. I'm a fourth-year graduate student in the Lightwave Lab. Artificial intelligence has become ubiquitous today. We see it in applications from speech translation to gaming to self-driving cars and so on. What really led to the growth of AI in the last decade has been the availability of enormous amount of data, as well as the growth of complex artificial neural network algorithms. But at the same time, the computational energy that you need to run these neural networks has also exponentially grown. In trying to find a better hardware, we look at the most powerful processor, which is the human brain. A brain is a vast network of about 100 billion neurons with about 10 to the 15 interconnections between them. And a brain can do about 10 to the 18 floating point operations per second, while only consuming about 10 watts of power. So if we compare this to a supercomputer, say the IBM Summit, it can only perform about a tenth of the operations that a brain can, while consuming about 1 million times more power. So this brings us to neuromorphic photonics, which is the perfect marriage between neural networks and light. So in our lab, we design and build these photonic neural networks on silicon chips, where we are trying to use the highly parallel distributed processing of neural networks and combine that with the high bandwidth, low latency, and highly energy efficient processing of light. Some sample projects that we have in our lab, designing fundamental photonic devices to designing large-scale photonic systems like the neural networks. And then we take it a step further and use these systems for real applications, such as RF fingerprinting, where we are using a neural network to process and classify incoming radio frequency signal in real time. And we also have another project where we are using photonic neural network based on an organic platform to be able to do a smart display for augmented reality applications. Here is a photonic chip that we designed in the lab and got fabricated in Singapore. It has about 5 neural networks on it, and for a sense of scale, you can see how small it is. It is about maybe a tenth of the size of this coin over here. One important thing about what we do in making these photonic circuits is to design the control for these circuits. And Wei Peng here is going to talk about how he does it.
Hi, I'm Wei Peng. I'm second-year student in Professor Prucnal's group. And as you may know, our group are doing research on silicon photonics, which we're making and testing the chip that's running by light. And to modulate the light on the chip, we're using tiny structures called microrings. And for each microrings, we need applied current to control the microrings. So we need to use a source meter such as this commercial bulky ones. But there are several tens of the microrings manufactured on the chip. So to accommodate that, have to come up with these custom solutions. As you can see here, when all the slots are occupied, we could have available channels up to 128. This powering up that large amount of rings, we could make all the fancy applications possible, such as a large vector matrix multiplication and neural network of several layers. Isn't that awesome?
So we use these neural networks that we build in our lab for real-world applications, such as using it for compensating for signal distortion over transatlantic communication system, or even using it for signature detection in radio frequency signals that my lab mate Josh is going to be talking about.
Hi, I'm Josh Latterman. I am a second year in the Lightwave Lab group. What I'm showing you right here is our setup for a Peach project, which is to develop a hybrid photonic FPGA device to do what we call specific emitter identification. Our goal is to be able to identify, given a series of identical transmitters, which one is transmitting a given signal based off of the minute imperfections in the design process. One of the big focuses of this project is high-speed classification, and that's where this device you see right here comes in. This is a FPGA board, and we are experimenting with the integration of FPGAs and photonic technologies. One of our experiments is maximizing the data transfer speed between FPGAs and photonics, which is going on right here. We are testing the speed at which we can communicate artificially generated analog signals between some of our devices and the FPGA board.
Thanks for your interest in our lab. If you want to learn more about any of our research projects, feel free to contact any one of us and we'll be happy to talk to you. Thank you.